Hello and welcome to the EMC live webinar, Limitations of Active Rod Antennas in Emissions Testing. My name is Belinda Stashikevich and I'm editor of Interference Technology, the creator of EMC Live. EMC Live is an online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related. There's no cost to attend. Join us for our other webinars this week. This webinar is presented by Roberto Grego, manager at NARDA Safety Test Solutions. This webinar is sponsored by NARDA. NARDA is the worldwide leader in research and development of EMF measurement equipment and holds 95% of all patents for EMF measurement. This webinar is one of many. To check out our others, visit emclive2015.com. A recording of this webinar and downloadable PDFs will be available on our website shortly. This webinar will be interactive. You will be able to ask questions and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the right-hand corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. And now Roberto will begin the presentation.
I will go through a topic that is quite well known in the EMC community, that is the use of the rod antenna. So I will not spend too much time on details about what a rod antenna is. Just a few hints. So rod antenna is a case of dipole antenna which had one of the monopole hidden or buried under the ground, so it remains a monopole only. First example was the Marconi antenna, designed for emission, of course. As you can see, this was one of the first transmitters. The other monopole, which constitutes the dipole, is the ground. And the ground acts as a reflector, so more or less like walking on a mirror. The rod antenna length, by definition, is optimal at 1/4 of the wavelength we intend to use it. Less something because of the propagation velocity in the wire. In this condition, the current and voltage flowing through the monopole have a sinusoidal distribution along the road. But in case we are using a wavelength much longer than the road, starting from 1/8 of the road length, of the wavelength, current and voltage curiously tends to be linear in distribution along the length of the road. And this characteristic will be used for the purpose in EMC. Now, speaking about the ground plane, ideally the ground plane should be something infinite. So, in order to form the missing half of the dipole. If the ground plane would be perfectly conductive and infinite, we would have a perfect pattern like the dipole. Instead, of course, there are limitations, even if we are using the ground, very wide ground. The radiation pattern of the rod antenna will be changed. So, in practice, ground planes, also called counterpoise, can have different sizes according to the application, and in any case they will affect the properties of the rod antenna, and particularly the radiation pattern. So an example is when you have a rod antenna mounted on the top of a car. Now, it is interesting for our purpose to see some aspects of what happens when we are going to use this rod antenna in EMC application. So in EMC, we are going to use the rod antenna as a receiving antenna of known characteristics in order to measure the radiated emission in terms of field strength in volt per meter. That is defined by standards. So standards say the rod length must be 1 meter or 1 meter and 4 centimeters. Also states the counterpoise size, for example, 60 by 60 centimeters. The frequency range, usually from a few kilohertz to 30 megahertz, in order to cover the communication bands, low frequency up to short wave. And the field strength range to be measured, so the limits not to be passed, and the detectors to be used in order to read the value of the field strength. Also, the standards define the grounding method and the distance of the antenna from the equipment under test. Last but not least, the standard also defined a common calibration method in order to assure the results will be the same. This table shows just some example of different standards with the different frequency ranges and different limits allowed for the emissions in those frequency ranges. Now we said we are going to use this rod antenna 1 meter long in the range from 10 kilohertz to 3 megahertz. So the wavelengths will span from approximately 30 kilometers to 10 meters. So our tiny rod will become behaving like a probe in a near field. This is the behavior, and as we have seen before, in this condition, the voltage distribution along the road will be almost linear. However, the characteristics, the complex impedance of the road respect to the RF field in this particular condition is showing that the self-capacitance of the road antenna is dominant on inductance and resistance. The electric length is half of the physical length, so we are speaking about half a meter. So we will measure a voltage across half a meter in practice. The assumption of linearity, as we said, below 1/8 of the lambda is matched. And of course, since we are going to use the unit dB microvolt per meter, in order to linearize to 1 meter, we will add 6 dB to the readings we will make with the spectrum analyzer or receiver. This is the equivalent, basic equivalent circuit of the short monopole. So we have a generator and the capacitor, so the self-capacitance in series. There is a formula for calculating the capacity of the rod as a function of the length and the diameter of the rod, and this formula provides a curve which shows that practically the capacitance is constant. It's a very low capacitance, few picofarad. Practically it's constant up to 10 megahertz approximately, and then it changed quite quickly. So the region we are interested in is the region in between 10 megahertz and 30 megahertz. Unfortunately, there are drawbacks in using the rod antenna EMC. So we have intrinsic drawbacks. That is the fact that we are not using very large counterpies. Then these counterpoise can be grounded or not. Anyway, we have an impedance of this bonding. The impedance of the RF cable, which is connected to the counterpoise and to the rod antenna, and the capacitive effects of the environment. So the antenna is nearby a wall or the UT, and there will be some capacitive effect. Also, and this is one of the aspects we will look into with more details, the geometry of the antenna changes mainly due to the coaxial cable shielding, which is acting as a, let's say, a structural additional element to the counterpoise. So we vary the geometry of the antenna. And this leads to the fact that we have the capacity of the rod and the impedance versus ground means we have resonances. Now, in this diagram, we see on the left the theoretical situation in which we have the variable self-capacitance of the antenna, for the reasons we mentioned before, the impedance of something which is connected to the load, for example, the cable, and the load is assumed to be purely resistive. In practice, we will have the situation on the right side. So we have a variable capacity, we have an inductance in series, and the load also has its own self-capacity. So it's a complex situation which is variable within frequency and within external conditions. So parasitic capacitance, of course. All those elements are contributing to the uncertainty of the method. So in other words, the rod capacitance changes as a function of this impedance, and the result is that we have a voltage divider dividing circuit which changes with frequency and with conditions that could be not under direct control or clearly repeatable cabling, grounding environment. By following, we see an example of a simple simulation of rod antenna structure connected to a piece of metal, a wire, that is the shielding of the coaxial cable, which is grounded at a certain distance. Of course, we could take in consideration several types of simulations. This is a very basic because time doesn't allow to do more. But anyway, it's representative of this interesting phenomenon. Here in the graph, we see the equivalent diagram. So we have a capacitor and an impedance which form this voltage divider, and the curves shows what happens at the different lengths of this external structure to the counterpoise. So we see, for example, that without cable we reproduce the curve we have seen before, so the ideal curve. But a simple meter of cable is going to change this behavior by creating a change of phase. So therefore there are resonances in this configuration. The longer the cable, the more sensitive is this effect. So we see here more and more resonances moving on lower frequencies as the cable is longer. Now, there are common countermeasures to reduce those resonances put in place in laboratories. I'm just resuming some. One is to shorten the cable image by grounding the counterpoise, or by increasing the impedance of this grounding by ferrite bits, or both, like in the example, or according to other standards, we have a connection and metallic sheet connecting the counterpoise to the setup grounding. Or in other cases, the counterpoise is left floating, totally floating. So every method has its advantages and disadvantages, of course. Now, the low capacitance self-capacitance we have analyzed before makes that the rod becomes a high impedance source. We have to measure, so we have to use a MOSFET preamplifier and impedance adapting circuit to match the 50 ohm output, which will be connected to the measuring instrument. Nothing special, indeed, but preamplifier is subject to saturation. So saturation because we are going to measure not simple pure signals, but we are going to measure disturbances that could be very broadband, very high in peaks. So there could be saturation in the preamplifier and maybe not recognize it. In addition, the MOSFET input can be damaged by electrostatic discharge, making the antenna a bit sensitive to handling, not mentioning the overloading, of course. In conclusion, dynamic range and sensitivity of this measuring system composed by the antenna, the preamplifier inside the antenna, and the external receiver or analyzer, the dynamic range and sensitivity, I said, are determined exactly by the preamplifier. So the preamplifier is a very important part of this measuring system. And since we measure broadband impulsive noise, it could be challenging for several aspects. In conclusion, the overall uncertainty may vary with respect to calculations, and this is the worst side of the story because, of course, something that can be foreseen can be compensated, but if there is no way to understand in advance what is going to influence the operation of a certain equipment, there is no way to compensate. So, if we put all those facts together, what we can get is that the emission measurements with the rod antenna, that is an official method of testing for several standards, may be affected by unpredictable changes in uncertainty. Standards and standard committees and the long experience in laboratories made that there are various methods used to mitigate those sources of uncertainty. However, without entering in taking a position, of course, which is not my purpose, it seems that not a single solution is the ideal one. So, as a matter of fact, standards are not telling the same solution and not giving the same instruction on how to use the road antenna. It happened that there are alternative methods that have been experienced in order to solve this issue. So one is thinking of eliminating the cable effect by replacing the cable with a fiber optic cable that is, of course, free of any influence on the antenna structure. And bringing the measuring unit inside the antenna, so there are no elements in between the antenna as a sensor and the measuring unit that could be a receiver or analyzer or whatever. It is interesting to see an experience made by Mr. Gold of General Dynamics. In order to check the comparison, to make a comparison between a simulation and a test with a cable and test with optical fiber transmitting the RF signal to the measuring instrument. You can see that the blue line, I hope you see the color as well as I can see, the blue line shows the measurement with the optical link, and this is the closest to the ideal, that is the line in the middle, while the red line is the measurement with the coaxial cable. So it is evident that there is a region of frequency range that can be very critical in that aspect. The other experience consists in replacing the cable with an optical fiber. So the cable issue is solved, but it remains another possible issue. And the other issue is that we are going to use electro-optical and optical-electrical transducers that, in case they are sending a RF signal in form of analog signal, they are subjected to some limitation. So the further experience is to improve the performances by embedding the receiving unit into the antenna. This is an example. This is a possible diagram of measuring receiver, for example, where we have a set of functions very well known, like the auto-ranging input attenuator, a frequency preselection, and the digital, the fiber optic link can be digital, so free of saturation, noise, and whatever. A system can also be self-calibrating, and what is interesting, also calibrated and in order to comply with the severe pulse response test as prescribed by the CISPR 16-1-1, that is the standard for the measuring instruments. So those functions are of course today possible by the large-scale integration available and digital technology. Last but not least, the calibration of the antenna can also be improved. So the calibration is normally performed by the substitution method. So we replace the rod by a capacitor. A RF signal is injected, and there is a termination to match the RF generator output, and then the voltage measured on the output of the capacitor is measured by the receiving unit. In case of this experimental integration, we can have also the possibility of using the CISPR pulse generator for calibration. So calibrating at once both the rod antenna and the receiving unit. Basically, this is more close to the reality because the antenna will be subjected to impulsive disturbances. In conclusion, and I'm going to end my speech, and thank you for your patience. If we want to improve the uncertainty of a rod antenna, it is demonstrated that we have to work on three basic aspects. The intrinsic drawbacks, as much as possible, the cable and grounding effects, so reducing the cable and grounding effects, and on the preamplifier side and calibration side. All those things work together can provide an improvement into the measuring method of using the rod antenna in EMC. So my speech is finished. Thank you again to everybody. Sorry again for the slow start, but I hope I finish quickly. If there are questions, I'm very happy to stay here and answer. Thank you.
Great, thank you so much, Roberto. We'd like to have a call for final questions. Please enter any last questions you may have in the navigation pane. We have received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, emclive2015.com or interferencetechnology.com. You can also email us at info@interferencetechnology.com with specific needs, and we can direct you accordingly. Roberto, here's a question for you. Are the rod antenna issues of common knowledge in EMC test laboratories?
Yes, definitely. I never found a laboratory completely, totally happy of the results. I would say that this is one of the most critical measuring methods that a laboratory can experience.
Great. Here's another question. Are there ongoing discussions on this subject among standardization committees?
Also, to my knowledge, yes. Of course, there are other people more entitled than me to talk about this point, but I know that there are discussions in order to improve the measuring methods, perhaps by using what we explained. I don't think there are physically much more methods to be used, but certainly there is. There are people working on that.
Great. Here's another question. The described alternative solutions are characterized by the higher degree of complexity. Are there disadvantages in it?
In principle, I would say yes. Every time you have more complexity in some equipment, you rise at least the risk of failure in general. But let's say that differently from even a few years ago, today the possibility of integrating on large scale RF equipment, RF circuits, and the large use of digital technologies allow to greatly reduce all the risks of additional complexity. So I would say the risk of the disadvantages, even in terms of reliability, then in terms of practical cost, for example, that is also one parameter to consider, they are not an issue today.
Great, thank you so much. We have received quite a few great questions we will try to address in the future. Roberto, thank you again for your time and expertise. Please join us next year for EMC Live 2016, which takes place next April. Webinar attendees, if you have any more questions we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website. We will also send a link to all participants shortly. Thank you for attending.
Thank you. Good evening.